So now we're going to talk about equivalence relations. So before we get to equivalence relations, we're going to start with just a relation. So the definition, a relation R from a set A to a set B is a subset of the Cartesian product A cross B. So let's look at an example of a relation. So let's see. Let's say our set A is the set 1, 2, 3, and B would be A, B, C. So an example of a relation from A to B, it's a subset of the Cartesian product. So I have ordered pairs here where the first element comes from A and the second element comes from B. So for example, 1A and 2C. That's a subset of A cross C, of A cross B. And from here we talked about the domain of a relation. It's all the first coordinate entries you have, where AB is an R for some B and B. So for example here, the domain of R would be 1 and 2. Those are our first coordinates appearing for our elements in R. And then we also had the range of R, which was the elements B and B, such that AB is an R for some A and A. So the range would be all of your second entries, your second coordinates. So A comma C would be the range in this example. Okay, and then from here we talked about a relation on a set A. So here you're only working with one set, and so it's a relation from A to A. We also discussed the inverse relation. R inverse, so it's where you flip the entries in your ordered pair. BA, where AB is an R. And so now let's talk about some properties of relations. Properties of relations. So we're going to focus in on relations on a set A. So a relation from A to A. And there were 3 different properties we discussed. The first one being reflexive. So remember that a relation on a set A is reflexive if X relates to X for every X in A. So every element in your set needs to be related to itself. The second one was symmetric. A relation on a set A was symmetric if whenever X relates to Y, then Y relates to X. And the third property was transitive. So a relation was transitive if whenever X relates to Y and Y relates to Z, then X relates to Z. So let's look at an example of a relation here. So let's say A is going to be the set A, B, C, D, and let's say R is the set A, is the AA, BB, AB, AD, BA, BB, and finally DC. And I want to know, is this relation, is R reflexive, transitive, or symmetric? Here, I usually do symmetric second, so I'll do symmetric and transitive. So let's start with reflexive. Is this relation reflexive? If you look through, you'll see AA is in your relation and BB is, but CC and DD are missing. So the answer is R is not reflexive since CC is not an R and DD is not an R. Now the question is R symmetric? So if you're looking for symmetric, go through your elements. AB, flip them, BA is in there. Now AD, if I flip it, DA is not in there. So R is not symmetric since AD is an R, but DA is not an R. And finally, let's talk about transitive. Is R transitive? R is not transitive since, let's see, AD and DC are an R, but AC is not an R. So this reflection was not reflexive, not symmetric, and not transitive. Let's look at another example here. So let's say I have a relation R is defined on C on the integers by A relates to B if either A divides B or B divides A. Determine which of the properties reflexive, symmetric, and transitive are possessed by R. So let's start with reflexive. So the question is, does A relate to A? Well, in order for A to relate to A, either A divides A or A divides A. Well, these are really the same statement. And yes, A divides A. So the answer is yes. R is, or I'll just say R is reflexive. And now let's prove it. So proof, let a be an integer, then a divides a, since a equals a times 1. Therefore, a relates to a, and R is reflexive. So now let's look at symmetric. So if I'm looking at symmetric, I'm assuming A relates to B. So I know from the assumption that A relates to B that either A divides B or B divides A. Now the question is, does B relate to A? Well, if B relates to A, then B divides A, or A divides B. But these are really the same things right here, just written in an opposite order. So I'm going to conclude that R is symmetric. And let's provide a proof of that. So assume A relates to B for two integers A and B, then by definition of the relation, A divides B or B divides A. Now, I can conclude that B relates to A since B divides A or A divides B. And that's the end of the proof that the relation is symmetric. Now the question is R transitive? So I'm going to assume A relates to B. So either A divides B or B divides A. And then I'm going to assume B relates to C. So either B divides C or C divides B. And the question is, does A relate to C? So maybe I'll write this. Does A relate to C? So does A divide C or C divide A? So you need to think of some examples. So if you look at a few examples, you'll see that A does not have to relate to C. So let's say we take A to be 2 and B to be 6. Then 2 relates to 6 since 2 divides 6. Let's take now B is still 6, and now I'm going to take C to be 3. So 6 relates to 3 since 3 divides 6. But 2 is not related to 3 since 2 does not divide 3 and 3 does not divide 2. So R is not transitive. And there's my counterexample. Right here is my counterexample.